Hi everyone, thank you for joining today's talk. My name is Seung, and today I'll talk about our word emoji. Let's briefly talk about the implementation of graph-traversal first. In graph-traversal, we pick certain vertices in a graph and then constantly traverse neighboring vertices in an iterative manner. To store the graph data structure, we often use a sparse matrix format such as CSR. If we look at the edge list of the CSR dataset, we can find it is composed of many sub-edge lists which are named as a neighbor list. The purpose of the neighbor list is to record the IDs of the neighboring vertices of each vertex. To distinguish between different neighbor lists in the edge list, we need to look up the vertex list, which contains the information of the indices of the neighbor list boundaries. Now, for the large graph datasets, because we need to process a massive number of vertices during the graph traversals, parallelizing the workload with GPUs can be beneficial. In this slide, we show a very simple example of graph traversal algorithm. In this algorithm, the for loop in the third line can be massively parallelized using GPU and significantly accelerate the overall workload. There are already several graph traversal frameworks such as cuGraph and Gunrock which extensively use GPUs to accelerate graph applications such as PageRank and breadth-first search. However, unfortunately, with an increasing size of datasets, not all graph datasets can fit into the GPU memory. In this case, the CSR dataset that we have shown in the previous slides must be stored somewhere else and accessed in runtime from the GPU. For example, ClueWeb12 graph has about 42 billion of edges, and this makes the total size of the edge list about 168 GB. Due to the sparse nature of CSR format, accessing vertices in the graph often leads to generating irregular data access patterns with a poor spatial locality. Since the DMA engines of the GPU are only optimized for large block data transfers, irregular data access pattern with poor spatial locality cannot get any benefit from the conventional DMA-based method. To bridge this gap, the PastWorks proposed several solutions. In Halo, a CSR reordering process has been introduced to retain the spatial locality vertices in graph into the CSR as well. Subway introduces a CPU-based gathering process where the CPU dynamically packs the neighbor list in an on-demand fashion to reduce the number of DMA calls. However, even with all these efforts, still the PCI bandwidth between CPU and GPU is not fully utilized, and this wastes the opportunity to further improve the execution time of graph traversal applications. The fundamental limitation of the previous works are that they keep trying to copy data in chunks to minimize the DMA call overhead, and therefore always the data must be readily coalesced in the CPU memory. In this work, instead of relying on the block data copy methods, we decide to utilize the cache line size access capability of modern GPUs. For the NVIDIA GPUs, there is a zero copy access capability, which allows GPUs to directly access external memory locations in a cache line granularity. With this capability, the address space of the external memory location is mapped into the GPU page table, and GPU can simply access the map location by doing pointer dereferences in CUDA codes. However, this is just a high-level idea yet, and we need to understand if this access method can fully utilize the PCI bandwidth in practice. In the following slides, we'll go to the lower level of the PCI traffic behavior of the zero-copy access and show how this access method can be exploited to speed up the graph traversal. First, let's quickly go over the test setup to analyze the PCI traffic behavior of the zero-copy access. In our Intel system with PCIe 3.0, we connected an NVIDIA V100 GPU and an Xilinx FPGA to the identical PCI switch. The FPGA logic was designed to and advertised as a large memory space to the GPU so GPU can generate zero-copy access to the FPGA. Inside the FPGA, we also added several monitoring logics to closely monitor the PCI traffic generated by the zero-copy access. The example application to monitor the PCI traffic was a simple sequential data access using GPU threads. However, we modified the permutation of thread groupings of GPU to observe in which grouping strategy we can get the best PCI performance. The first strategy is to let each thread to sequentially access a single large chunk of data. In this case, we observe that each thread ends up generating 32 bytes of requests over PCIe. If the data type used to access is 4 bytes, then this means each PCI request can serve up to 8 sequential accesses. When we look at the bandwidth measurement of this method, the PCI bandwidth is far lower than the optimal case because the request sizes are too small and the overhead of PCI requests becomes quite significant. The second strategy is to merge the data access into a warp granularity. When the threads in a same warp access sequential data, we find the PCI request size can be merged up to the size of 128 byte. With 120 byte requests, we find the zero copy access bandwidth nearly reaches the peak bandwidth of PCIe. However, one thing to note is that the zero copy accesses should be aligned to the GPU cache line size, which is 120 byte. When the threads access a sequential chunk of data, which is crossing the boundary of GPU cache line, the PCI request is split into multiple requests and the PCI bandwidth decreases again. Now, based on our observation in the previous experiment, we implement a zero copy access based graph traversal algorithm, EMOGI. In EMOGI, we store the edge list of the input graph in the CPU memory, and it is never migrated into the GPU memory. All access to the edge list are done through the zero copy accesses. At the bottom left of this slide, we show the baseline code of the graph traversal using GPU. In this case, because each neighbor list is traversed by a single thread, we end up generating numerous 32 byte PCI requests even if the neighbor lists are longer than 128 byte size. In the optimized version of code, now the traversal of each neighbor list is done in a group of 32 threads instead of a single thread. To mitigate the unaligned memory access issue, we also forcefully adjust the starting index of the edge list traversal to the closest previous 128 byte memory address boundary. These two changes from the original baseline code can significantly increase the chance of generating larger PCI requests and saturate the PCI bandwidth. To evaluate the effectiveness of our method in detail, we picked BFS as a case study example. The naive implementation is the baseline code without any optimizations. The merge implementation includes the warp grouping optimization for the coalesce accesses, but it does not include the alignment fix optimization. And finally, the align implementation includes both the merging and the alignment optimizations. UVM method uses NVIDIA's UVM page migration method, which transfers data in a page granularly instead of a cache line granularly. When we take a look at the chart on the left, we can clearly see the impact of the optimization that we added. For the naive case, most of the PCI read request sizes are about 32 byte. With the merge optimization, the number of larger PCI read request sizes significantly increases. And with the alignment optimization, the number of 128 byte PCI read requests increases up to 90% of the total PCI read requests. The benefit of generating larger PCI requests in terms of bandwidth is shown in the chart on the right. With the naive implementation, we can reach only about 5 GB per second of PCI bandwidth. However, with all optimization, the bandwidth increases to about 11 to 12 GB of bandwidth, which is almost identical to the peak DMA bandwidth that we observed. For the UVM case, because the page migration requires additional step processed by CPU, the UVM method achieves a low PCI bandwidth with the application with an unpredictable data access pattern and frequent page evictions. When working with applications with unpredictable data access patterns, it is also important to restrict the available I/O bandwidth only to the useful data. In case of UVM, because UVM can only access data in a page granularity, accessing small neighbor lists in the CPU memory also results in bringing a bulk of unnecessary data as well. On the other hand, the EMOGI's maximum data access granularity is limited to the GPU cache line size, and it is easier to perform the pinpoint data access from GPU to the CPU memory. As we can see on the chart on the left side, UVM method is causing a huge amount of I/O amplification over PCIe, while EMOGI can effectively limit the data access only to the necessary portion. In terms of overall BFS execution time, the most optimized version of EMOGI is about 3.56 times faster than the UVM case. When we compare EMOGI with the previous out-of-GPU memory graph traversal solutions, EMOGI shows better performances in all cases. For the detailed experiment setups, we have thoroughly described in our paper. Thank you for listening to our talk, and please let us know if you have any questions. We have also open sourced our code in the following GitHub repository, so you can directly go to the following link and get access to the source code. Thank you.